Hello, I'm Cian Wilson. I'm a computational scientist here at the Department of Terrestrial Magnetism at Carnegie Institution. That means that I develop and support computational software for the scientists here who are engaged in research projects that require computational modeling. At AGU, I'm going to be presenting some work we've been doing dealing with carbon sequestration, so looking into how we can potentially take carbon from the atmosphere, react it with rocks, and secure it away in that manner so that it's now solid and no longer in the atmosphere. One of the problems with doing that is that rocks at low temperatures near the surface of the Earth don't like to react. You end up reacting the surface of the rock, and that creates a film of material around the surface of the rock that prevents the reaction from reacting all the way through the entire rock. But when we go out into the field, we see examples of rocks that have been completely reacted right to their core. So these are some examples from Oman, where we see rocks that have been carbonated, have been reacted with carbon all the way through. And what we see in them is that they are highly fractured, and associated with these fractures are these reactions. So one of the theories of what's happening here is that as the reaction progresses on some surface of the rock, the volume of the rock, the original rock and the carbon, is different to the volume of the product of the reaction. And that volume change generates stress inside the rock, which leads to the rock fracturing, exposing fresh surfaces for the reaction to continue and to continue pervasively throughout the entire rock. We presented some initial simulations of this process previously at an AGU, and these are some simulations of that. So what's happening here is we're imagining that we have an elastic rock, kind of like a sponge, and in the holes of the sponge there's fluid, carbonated fluid, and that is reacting with the rock around it. And then what we're looking at is the stresses that we can generate within that rock. What we find is that the stresses that we generate far exceed the sort of strength of the rock, and therefore, if we weren't just modeling this like a sponge, like an elastic solid, we would expect that we would be generating fractures within this rock. So what I've been doing over the last few months is trying to work out how we can incorporate that fracturing process into our models. To do that, I've simplified the models quite a bit, and I'm sort of ignoring the reaction. And instead, I'm modeling a cylinder of rock. Again, a sort of sponge-like elastic rock. And in the center of this cylinder, there is fluid that is being pumped into the rock at some high pressure. And because it's like a sponge, that fluid is migrating into the rock through this inner wall. As the fluid migrates into the rock, just because of the fluid pressure, it generates stress within the rock and causes fractures to form. And if I zoom in here, that's what these red lines are. These are fractures that have formed within the rock. And each quadrant, each quarter of this simulation has slightly different parameters for that rock. So we can generate different fracture patterns depending on the parameters we assume. So that's what I'm going to be presenting at AGU. The hope is that we can take this fracture modeling mechanism and combine it with some of our reactive flow models and model the whole process together in the future. Thank you.